Okay, there's some notes to take. Okay, this graph, concave up or concave down?
Concave smiley face.
Concave smiley face. So concave up. Actually, like this. Okay, so by definition, we are concave up when the slopes, not slops, the slopes, f prime, are increasing. When our slopes are increasing. So here, if you look at this side, our tangent slope, very negative, less negative, 0, and more positive. So by definition, when our slopes are increasing, that is concave up, which means the second derivative is positive. Is positive, i.e., here the slopes are increasing. So it's very negative here, right? And it's becoming more and more positive. The slopes isn't necessarily positive. Yeah, it's not saying the slope is positive, it's saying the slopes are increasing. Yeah. And so second derivative is greater than 0. Okay, so if our slopes are increasing, that would be second derivative. That means that our second derivative is above 0. We talk about it holding water, right, versus shedding water concave down. Okay, so here, this is a very positive tangent line. Approaching, it goes to 0, and negative, and more negative. So here, the slopes are decreasing. Okay, so that means the second derivative is negative. So our second derivative is less than 0. So sheds water, right? Or I like to think of it as happy face or sad face. Right? I don't know. Or just concave up, concave down is a good way to think of it. Okay? Craig? Changes in concavity always occur at critical values for the second derivative. So when our second derivative is equal to 0 or undefined. So that's where we can have a change in concavity. Why is Mr. Trimble say concavity? Concavity. Yeah. Oh, yeah. Okay, so here, this is concave up. Here, this is concave down. And what this point, that would be the point where it's changing from concave up to concave down. It has a special name. It's called an inflection point. Point of inflection. Same thing. Point of inflection point, point of inflection, tomato, tomato. Okay, so again, here this guy is concave down, concave up, and another inflection point.
Well, when is it like, when it's DNEs?
When the denominator is 0. Right? So that happens, like that would be an asymptote. An asymptote. Okay, so the verse is not always true. Critical values do not always mean a change in concavity. Yeah. So you talked about multiplicity today? Last unit? Yeah. There might not be a sign change for f prime. So it doesn't have, right, an inflection point. If it doesn't have a sign change in our second derivative, then that's not an inflection point. Okay. Point of inflection. Inflection. Point of inflection. Okay, so I was going to write this all out, but should I determine concavity, find the critical values at the f prime of x by setting f prime of x equal to 0, then test on the number line. You know how to do that, right? Okay, so let's look at this graph. I'd like you to identify the regions of concavity and the points of inflection. Okay, so you're going to estimate. So the first part here is concave up. So somewhere around here, because here's concave down, this would be a point of inflection or inflection point. I like using inflection point because then I can just write IP.
Which is cooler sound. Yeah, always better than
You go ahead and write whatever you want. Okay? So what is this guy? No, not yet.
No.
Right there, right? So this guy here, from here to here though?
That is concave up.
Thank you. Concave up, concave down, and then that's right. That's undefined there. Here's concave down. Here's concave up. Would this still be an inflection point?
No.
It's not differentiable, but it's still an inflection point. A point exists. Limit. Yeah.
Why is that an IP?
Because it's the point. It's approximately somewhere in here. The point where it changes from concave up to concave down.
Oh, so it's just where it changes.
Yeah. So we're estimating here, right? Concave up, this is concave down, so this is about the point where it switches. So that's when our second derivative equals 0.
I thought the inflection point was only when there's x to the 3.
Well, you're in polynomials, if you look at it, right? A third degree, a fifth degree. Yeah, but these are functions that are not necessarily polynomial or not polynomials, right? So you were learning about it in terms of polynomials, but we can also look at other functions that have them that aren't polynomials. Okay, woo. Okay. State the intervals of concavity and the points of inflection for the following. So here's multiplicity of 3. So first step, find your first derivative. What is it? Plus 48x minus 5. That's just going to give us increase and decrease. We want second derivative for when it's concave up, concave down. That's the last unit. So 12x, no, plus 48. So our critical value, I can factor 12 out, and we get x plus 4. Yes. So what's my critical value? Negative 4. So we're going to label, this is y double prime. Label your interval test. So your first derivative, second derivative, guys. Okay, a critical value of negative 4, and we want to do a test. So pick a number less than negative 4. Thank you. Plug it in, and that's going to give us a negative. Negative 5 plus 4 is negative. And then greater than negative 4 will give you a positive. So we can say we are concave up when?
Greater than or equal to negative 4. Not equal greater. No, I'm completely wrong.
Oh, sorry, I'm completely wrong.
Oh.
I was thinking down, and I wrote up. Concave up, negative greater than, yeah, negative 4. And concave down. Thank you. Yeah, up is positive, down is negative. Concave down, negative infinity to negative 4. Okay, we also want to find inflection point. Where's our inflection point going to be then? Where it switches from positive to negative. So we actually have to find the value at negative 4 comma something. I still struggle with them. No, you guys are so great. Okay, 2 times negative 4 cubed. Oh, sorry, exponential functions. 2 times negative 4 cubed plus 24 times negative 4 squared So we always go back to our original equation to get our actual point. Yeah, 255. You guys, I'm really slow with that virtual one. Yes. Those were the days. Those were good days. Those were good days. Yeah, I don't know. I don't have any competition anymore. Just kidding. Okay, analyze and sketch the curve. All right, we're going to add what we know and put it all together. Now, luckily, will this have any asymptotes?
It sure won't.
Right away, it won't. Sure won't. Why? Because it's not what type of expression? Rational equation, right? It's not a rational equation. There's no fraction in here. No.
How would you have an answer?
No, I know, but why? So what is that? What rational?
Rational is fraction. Fractional equation.
You didn't know.
Ratio. Okay. So let's start with intercepts. Intercepts. Okay, start with the x-intercept. No, let's start with y. What's the y-intercept? 0, 0. X-intercept. That's one of them. We need to factor. Plus and minus, so 0 plus or minus root 8. So that would be 0, 0, root 8 and 0. I'm sorry. It's just more interesting. Okay. Difference of opinion. Max mins. How do we get our max mins? Y prime. Same way we always do. Okay. 4x cubed. See, you're getting really fast at driving now, hey?
Oh, yeah.
Yeah. Okay. So factoring this guy, 4x we can pull out. Hey, guess what? Well, we have a
Difference of squares.
difference of squares. So, critical values. 0 plus or minus 2. Okay, so I'll slow down.
Oh, wow.
We have all day. Slow it down. You want what?
Okay. So, what are we going to do with our number line? I'm going to slow this down.
I'm good. No more slow.
Okay, so I'd like you to start labeling your number line. So because there's different interval tests we're doing. Which one are we doing? Y prime. Okay. Critical values?
0 and plus or minus 2.
You going somewhere, Cody? Oh, okay.
I'm so confused.
Me too. Okay, we need to go ahead and go with our critical value to our test, our interval test. So, okay, minus 3, I guess. Sound good?
4.
Negative 4. Okay, 4 times negative 4. Negative. Negative 4 minus 2. Negative. And negative 4 plus 2. 3 negatives.
Negative.
It's a negative. Since last time I checked. Unless they've changed the rules on that one in the math board. Okay, at negative 1, I guess, between negative 2 and 0. 4 times negative 1. 4 times negative 1 would be a negative. Negative 1 minus 2. Negative. And then a positive. Positive 1. Positive times 1 minus 2 would be negative 1 plus 2. Positive, so negative here. And last, positive, positive, positive. Okay, so we can say, when are we increasing?
Between 2 and 0 and 2 and infinity.
Okay, so increasing 2 at -2 and 0, union to infinity, decreasing all these. Okay, negative infinity to -2, 0 and 2. What else do we need in this guy? Okay, what else is important here when we do max mins? We did the increasing, decreasing, and you also actually have to find the points of maximum and minimum. You might want to draw the lines, right? We have decreasing, increasing, decreasing, increasing. So at -2 and 2 would be a local min. So local min at -2 comma something and +2 comma something. Can somebody plug those in?
Okay.
Thank you. To the original. Get the points. Are we all like okay right now? Yeah? Okay.
I feel like we've done this like
-16.
Yeah, it's like really repetitive.
-16.
-16. Both of them?
no, maybe.
Woohoo. Okay.
You knew that. You must
And max at local max at 0. We already know that point. 0, 0. Okay. So now that we have our max and mins done, increase, decreasing, we can go to our second derivative. We're going to have to start doing domain and range for our graphs. What would our domain be in this one? It's a polynomial? Yeah. So remember we did that stuff with domain and range in pre-cal? Okay, range, well, we know our minimum values, but we can also figure that out later. -16. Well, yeah, we do. Because it's a degree 4.
Oh, we do.
Right? So our range would be greater than, so -15. Oh, opening up or down?
It's opening up.
Opening up. Right, because they're dealing with 4th degree. Vertical asymptotes, horizontal none. So let's do this guy.
Wait.
Wait.
The range should be a square bracket now for the -16.
Thank you. Oh, somebody see those little things. Good eye. Good eye. Okay, second derivative. We'll go off of our first derivative. We'll go off of this guy. It is rude. Okay, 12x² minus 16. Do I have to explain how to get the second derivative anymore?
How to get the second derivative? No.
From the first derivative, we're good?
Although I have no idea what to do now because I forget what we did.
Okay, so critical values again. So factor. What can we factor out?
We can factor out a 4.
4? Yeah? Thank
Bye,
you.
Trina.
Hi, Trina. Okay. She'll like that. Okay, 3x² minus 4. You guys okay? Okay, critical values. So to get this critical value, you might just want to solve it for 0.
What's that squiggly?
Which one? This guy? The square.
Oh, okay.
Okay. So add 4, divide by 3, and then square root. Add 4, divide. Oh, well, it's not a critical value. It's not affecting us, right? We want when our second derivative equals 0. Yeah, sorry. So x equals, if we square root both sides, plus or minus 2 over root 3. right? Because we can square root 4, which is just 2.
I was really confused there.
So now another number line. Okay, so we have our negative 2 over root 3. You might want to figure out what that is as a decimal.
It's going to be a number.
It's probably root 3 is smaller than 2. So 1.15. Okay. So here, let's go with negative 2 then, I guess, for our test. So 2 squared, 4 times 3 is 12, minus 4 is a positive, okay? 0, plug in 0, give me a negative, and then put, well, this would be the same. 10, sure, still be positive. Okay, so that tells us 3 things. When we're concave up, when we're concave down, we can get our inflection points. Okay, so here is concave up, concave down, concave up. Yeah, U for up. It's an N. Okay. Union 2 root 3 to infinity. And concave down. Pretty much. Yes, unit kind of just slowly builds on itself. Concave down, negative 2 over root 3. All right, inflection points. Where are my inflection points? Negative 2 root 3. We have to plug those in. And 2. Oh, gosh. We need to plug this into our calculators. Someone's got to do it. Or.
I have it.
Okay, well, it's really easy. It's a small function. Let's just store this function, right? So I'll go. He made you afraid of what? Okay, so store as x.
What did you do? You took that calculator and you accidentally made it really big. It was just the whole screen, and you couldn't get rid of it.
How can you see no statement?
Okay. So math. I know. Negative 80 over 9. The original, right? Because we want the point, the y value, the actual y value. Yeah. Yes? So then it'd be a decimal. You'd give me a decimal. Right. If it's, but really even for this, like I'm being lazy, and so I shouldn't be, but this isn't that hard to plug this in, right? This function, because we're doing, what is it, 2 over root 3? Power 4 minus 8 times 2 over root 3 squared. And these are going to give you nice numbers.
So won't it just be like 8 over
2 to the 4 is 16.
16 over...
So you square it first, it's 3, and then 9. Minus, so that would be 8 times 4 over 3. Right, so this one is actually not so bad. And I won't get, if it's really ugly, I'll even tell you, like, to 2 decimal places. So, yeah.
And then if you get a nice number,
Yeah.
Just to be clear, first derivative, you get maximum in. Second derivative, you get inflection points, and then concave up, concave down.
Yes.
So what do you get for third derivative? They scroll down. Sure there's
Nothing,
something?
really.
And then you just have to put all those into the main to get it.
You always go back to the original to get the actual point.
And that's how you get the original for it.
Leave it down. Oh, we didn't even do it.
Okay, so we have to do this guy, but it's the fourth and it's square, so it's the same thing. Right? The sign won't affect it. Okay, so that was all in one question. Woo! We have to draw it. There's room on the next page to draw it. Yay! Okay. Let's do the best that we can. I might need your help.
Example 3 is in the textbook.
Yeah?
Make it not in the textbook.
It's not part of your homework.
No, but like it's what?
It's a good question. I can't believe that. Yeah. Okay, so we know we have a 0 here, plus or minus root 8.
How are you doing this?
Remember our zeros?
This is the previous.
Yeah, we're just sketching it. We're still, okay? So where's our minute? We have negative 2. Root 8. It's like close to 2, isn't it? 9 is, no, it's closer to 3. Yeah, because root 9. So like right there is root negative 2 and 2. My scale's a little off. Okay. Okay, what was our minimum value? What do we get for our min? Negative 16? Okay, so negative 16 and negative 2, negative 16, positive 2. Where were our inflection points? What y value? We had, what's 2? Oh, it was like negative 1 point something, right? So this will be 2 over root 3, 2 over root 3. I think it's more over here. And our inflection point went all the way up to, actually I have it here, 8.88. So 16, 8 repeating. Oh, thank you. Negative 80 over 9. Okay, so we have an inflection point here, inflection point here. 0, 0. Okay, there's our points. And here's a point. So I'm going to highlight it. Point here. Okay, so we have to be careful because we need to be careful of our concave up and concave down, right? So concave up all the way, sorry, be very careful with this, to here. Now it's going to become concave down, right? From negative 2 root 3, there's our concave down, now our concave up. Something like that. So review from pre-cal, this would be an even or an odd function? Even. Yeah. Because it's reflected in the y-axis. Okay, I need you to open up your textbooks to page 230. I have extra ones on the side table if you need one. I need one too. There's 5 textbooks on the side here. Do you want to just borrow one? Oh. Share? Do you want to share with the buddy? You should be bringing your textbooks to class, right? Right? Every day. Okay, 2:30. I lost my page, sorry. 2:30. Okay, number 7. I'm going to write out the question. Here it is. Okay, 7a. So it says f prime of x, guys, is greater than 0. You might want to write this down too. For x between 0 and 1, f prime of x is less than 0 for x greater than 1. Okay. So what we're going to do is we're going to sketch the graph that satisfies all the following conditions. Okay, so first off, let's talk about what are they telling us here? Are we talking about, what are we talking about? Concave up, concave down, increase, decrease, max, mins, right? We're dealing with the first derivative. So critical values that they kind of give us here, 0 and 1. So this is what they tell us. They tell us that between 0 and 1, it's increasing. It's above, greater than 0. Okay? And when it's greater than 1, it is decreasing. So we know what's happening at 1.
It's a
Up, down. There's a local max at x equals 1. Okay? Tells us something. Let's look at the next piece of information. So the next piece of information is the second derivative is less than 0 between 0 and 2. And it's greater than 0 when x is greater than 2. Okay, so critical values here, 0 and 2, and we're dealing with our second derivative. So what do they tell us? Between 0 and 2, what do we have? Concave down. Yeah, because second derivative. And then greater than 0, or greater than 2, sorry, concave up. So what does that mean? There's a point of inflection. Point of inflection at x equals 2. Soon. Okay, they also tell us something else. See, they say the limit as x approaches infinity for our function is equal to 0. What does that mean? Rational function. Okay, so bottom degree is bigger than top. And for our graph, what is that form? What is that? Okay, horizontal asymptote at y equals 0. All right, the last thing they say is f of negative x equals negative f of x. What does that mean? What does that mean for all x? Close, not even. Well, it's odd. So it's, where is it symmetrical about? The origin. The origin. So this is an odd function. This is from pre-cal. Symmetrical about the origin. So if we can actually graph everything greater than 0, then we can easily get less than 0. And that's why they only give you half the information. Okay, so let's try and sketch this graph. Okay, so our critical values were 1 and 2. Because it's symmetrical about the origin, we're going to have critical values of -1 and -2. Okay, what else do we know?
We know there's a local max at 1.
Okay, there's a local max at 1. 1 somewhere. 0, 0. 'Cause, yeah,
And at 2, there's a point of inflection.
point of inflection. So it's concave up all the way till, might make this a little higher.
Wait, it's concave.
Concave down. It's concave down. Thank you.
Concave down.
Concave down, and so this is going to be an inflection point here. So we have concave down. Oops. Concave down. Inflection point now becomes concave. Up. And it's approaching what?
0.
0.
How is that possible? Oh, yeah, it is.
Okay. So if it's symmetrical about the origin, what does that mean at -1? Local. So this is a local max. It'll be a local min. Be a local min. And we'll have an inflection point at -2. So now it's going to be concave up to -2, and then it's going to be concave down. It's symmetrical about the origin. So that means it's like rotated 180 degrees would be the same. Yeah. Okay, so here's the thing. The assignment for today's lesson is actually really short. It is, yeah, it was 2 and 1, that's why. Okay, page 229, which is right the page before. So number 1, which is really quick, 2 left.
2 left.
Okay, please do, for the left, even do at least 4. And then, yeah. So you're going to get, if you get this done, you can go. And 4. So for sure 4. Let's just go 3 and 1. So I had initially assigned 3, I and, well, there's actually 1, 2, 3, 4, 5, 6 in the left column there, A, C, E, G, I, K. Do it to choose 4 of them.
Or 5, or 6.
Yeah.
Oh, of number 1.
Of number 2
Of number 2.
on the left column. Look at it. Turn the page over. Page 229. Okay. 3 and 4 and 4. So this was the original assignment.
There's only 3 in the left.
Choose one of these. Okay. So if you get that done, you can go. So show me it done, you can go.